continue our discussions on what is light. In the previous lecture, we had discussed the evolution of the corpuscular model of light and also the wave theory of light, which was put forward by Christian Huygens. Today, we will start our discussions with the electromagnetic nature of light waves, which was put forward by Maxwell, and the light quantum, which was introduced by Einstein in 1905. So, this diagram on the left represents an electromagnetic wave, associated with which is an oscillating electric field and also an oscillating magnetic field. And on the right is a photograph of a young girl from various number of photons. So, each dot on the photograph represents the photon, which is essentially the light quantum as introduced by Einstein in 1905. Now, as we had discussed in the previous lecture, we had discussed the interference experiments, where we could establish that light was indeed a wave phenomenon. So, the wave nature of the light was established in the beginning of the 19th century, but the main question was, how could it propagate through vacuum? Around the same time, the laws of electricity and magnetism were getting developed. We had the Faradays Law, according to which a changing magnetic field produced by an oscillating magnet could induce an electromagnetic force and result in a current. So, physically a changing magnetic field produces a changing electric field. This was Faraday's law, and which was put in the form of an equation by Maxwell. Then there was this Ampere's law, according to which if I have a conductor carrying current, then surrounding it there is a magnetic field which is created. So, we have a conductor which carries a current I and which produces a magnetic field surrounding that. This was first observed by Oersted and then put in the form of a law by Ampere, which was put in a mathematical form by Maxwell. Maxwell also said that not only a current produces a magnetic field, but a changing electric field between the plates of a condenser, for example, also produces a magnetic field. When a capacitor gets charged, then there is a changing electric field here between the plates of a condenser. There is vacuum, let us suppose there is vacuum between the two plates. So, there cannot be any ordinary current flowing between the two plates of a condenser. There is a changing electric field which produces a magnetic field. So, this changing electric field was named as the displacement current, which resulted in the production of magnetic field. So, there was a symmetry in the laws of electricity and magnetism, as was put forward by Maxwell, that a changing, not only a changing magnetic field produced a changing electric field, but a changing electric field also produced a changing magnetic field. So, Maxwell wrote down all the laws of electricity and magnetism in the form of 4 equations. They are slightly complicated, and I am not going to write all those equations, but I am going to only say that the equations describing the laws of electricity and magnetism were put forward by Maxwell around 1864 and are known as Maxwell's equations. These equations are based on experimental laws, and so therefore, Maxwell's equations cannot be derived, and these, as I mentioned, was put forward around 1865 by Maxwell in one of the classic books in physics on treatise on electricity and magnetism. Now, in these equations, if we substitute an expression for an electric field as given by the above equation, it says that electric field, we assume an electric field in the x direction, x cap represents an unit vector in the x direction, E0 is the amplitude of the electric field, and this is sine of kz minus omega t. So, it is a wave like solution, as we had discussed in our last lecture. This sine or cosine of kz minus omega t represents a wave. So, if we substitute an equation of this type in Maxwell's equations, we would get that the magnetic field will be in the y direction and will have a same z and time dependence as the electric field, where the amplitude of the magnetic field H0 is given by k divided by omega mu 0. As we had discussed in the previous lecture, k is equal to 2 pi by lambda and omega is equal to 2 pi nu. Lambda is the wavelength and nu is the frequency, and mu naught represents the magnetic permeability of free space. Similarly, if we substitute this expression for the magnetic field in Maxwell's equations, we would get the corresponding electric field as obtained by substituting this in Maxwell's equations will be given by this. So, a changing magnetic field produces a changing electric field, and as we had shown in the previous slide, that a changing electric field produces a changing magnetic field. Both, you cannot have an oscillating electric field without creating an oscillating magnetic field, and vice versa. So, if we substitute this expression in the Maxwell's equations, which describe the laws of electricity and magnetism, and if I assume the H vector to be along the y direction, y cap is the unit vector in the y direction, then the corresponding electric field will be given by this. So, an oscillating magnetic field will result in an oscillating electric field, where the amplitude E0 is related to H0 through the following equation. So, thus we get two set of equations. H0 is given by this and E0 is given by this. So, if I multiply these two equations, then I get k square by omega square epsilon mu 0 will become equal to 1. And so, therefore, omega square by k square, I take omega square on this side and k square on this side. So, omega square by k square becomes 1 over epsilon mu naught. And so, therefore, the velocity of the electromagnetic wave, which is given by omega by k, is equal to 1 over under root of epsilon mu naught. So, this was a remarkable contribution by Maxwell. He said he wrote down the laws of electricity and magnetism in the form of 4 equations, and he showed that wave like expressions, equations of electric and magnetic field satisfy these equations. And so, therefore, he predicted the existence of electromagnetic waves, that the solutions of the Maxwell's equations give rise to waves. And so therefore, he predicted the existence of electromagnetic waves, and that the velocity of these waves he predicted would be equal to 1 over under root of epsilon mu naught. In free space, epsilon is the dielectric permittivity of the medium, something like a dielectric. In free space, epsilon has the value epsilon naught, and as we know, the value of epsilon naught is equal to so much, and mu naught is 4 pi into 10 to the power of minus 7 in MKS units. So therefore, if I substitute this, I get a value which is 3 into 10 to the power of 8 meters per second. So once again, Maxwell predicted the existence of electromagnetic waves, and from his equations he derived an expression for the velocity of electromagnetic waves in vacuum, and he predicted that the velocity of the electromagnetic waves was about 300 million meters per second. This was around 1861-62. At that time, the French physicist Fizeau had determined the velocity of light in air, and that value was also close to 300 million meters per second. So Maxwell said that these two numbers cannot be accidentally equal, and therefore with faith in rationality of nature, that these two numbers cannot be accidentally equal, he said light must be an electromagnetic wave. So I will repeat my argument, and this is one of the most important arguments in the development of science, not only of physics but science. Maxwell wrote down the laws of electricity and magnetism. From these equations he showed that wave-like expressions for electric and magnetic fields are solutions of these equations, and so therefore he predicted the existence of electromagnetic waves. He could calculate the velocity of the electromagnetic waves in vacuum, and he found out that the value of the velocity of electromagnetic waves that he predicted was very close to the velocity of light waves, as was measured by Fizeau. And then he said these two numbers cannot be accidentally equal, and therefore light must be an electromagnetic wave. And so therefore around 1864, in his famous book, Maxwell predicted the existence of electromagnetic waves and said that light itself is an electromagnetic wave. So in free space, you have an oscillating electric field which creates an oscillating magnetic field whose amplitude is proportional to epsilon 0. We showed that. So if E0 is 0, then H is all. One field cannot exist without the other. Both of them have to exist. If the propagation is assumed to be in the z direction, if the electric field is assumed to be in the x direction, then the magnetic field is in the y direction. So therefore, the propagation direction is at right angles to the direction of the electric field and the magnetic field, and so therefore the waves are said to be transverse. So this is how these are the two equations describing the electromagnetic wave. An oscillating electric field produces an oscillating magnetic field. An oscillating magnetic field produces an oscillating electric field. That is how fields propagate through space. The concept of fields was first put forward by Michael Faraday, and therefore the fields produced by a charge can exist even in vacuum, and these oscillating magnetic fields will produce an oscillating electric field, and oscillating electric field will produce an oscillating magnetic field. That is how electromagnetic waves can propagate through vacuum. If I have a charge in vacuum, then it produces its electric field even in vacuum. And if I make the charge go up and down, then the electric field will also change with time. Associated with that changing electric field will be a changing magnetic field, and associated with the changing magnetic field there will be a changing electric field. So, therefore, the velocity of the electromagnetic waves is about 300 million meters per second, and Maxwell said that light itself is an electromagnet. This is said to be one of the greatest syntheses in the development of science, that optics, the study of light and the study of electricity and magnetism are form come under one umbrella. It was only in 1887 that Heinrich Hertz generated electromagnetic waves by electrical circuits, and he allowed the electromagnetic waves to fall on a metal screen, got them reflected, and found out and obtained similar to stationary waves on a string. So he could determine the wavelength and the frequency, and from that he showed that the velocity of the electromagnetic waves was the same as the speed of light. And so, therefore, it was very soon established that light was indeed an electromagnetic wave. So, by the turn of the century, by the turn of the 19th century, people finally thought, scientists finally thought that one finally understood what light really was, that light was an electromagnetic wave, and because a changing electric field produces a changing magnetic field, that is how the electromagnetic waves propagate through free space. So, this happened, this was around the end of the 19th century. So, this is the entire, which I had shown in my last lecture, this is the entire electromagnetic spectrum, from gamma rays to X-rays to ultraviolet to visible region of the spectrum to infrared to microwave to the radio waves, to the waves that you receive on your cell phone or on your TV. They are all electromagnetic waves. They all travel with an identical velocity in vacuum, and the visible portion of the spectrum, to which the retina of our eye is sensitive, forms only a very small portion of the electromagnetic spectrum. So, the gamma rays have a frequency of 10 to the power of 20 hertz, and radio waves have a frequency of about 10 to the power of 6 hertz. And as I had mentioned in my previous lecture, the visible region of the spectrum has a frequency of about 10 to the power of 14 hertz, which is about 100 terahertz. So, this is the velocity. If I have a dielectric which is characterized by the dielectric permittivity epsilon, then the velocity of electromagnetic waves is given by this, the velocity of light in free space is given by this. So, the refractive index of the medium, which is given by C by V, is epsilon by epsilon naught. So, then light propagation through solids, liquids, everything was studied, and Maxwell's theory was found to be extremely successful. Max Planck had said, Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. In fact, indeed, Maxwell's contributions are for all times remains supreme. I mean, he made tremendous contribution to electromagnetic theory. So, this is my X polarized wave, in which the electric field is associated with this electric field. There is a magnetic field. So, I am right now not mentioning about the magnetic field. If I have a dancing electric field in the x direction, we produce what is known as an X polarized wave. If I have a electric field which is produced in the y direction, then you have what is known as a Y polarized wave. The electric field oscillates in this direction. For a Y polarized wave, the electric field oscillates in the Y direction. And you can also have a circularly polarized electromagnetic wave, in which the electric field at a particular point rotates on the circumference of a circle. You can superpose two light waves and produce a circularly polarized electromagnetic wave. So, what moves on the circumference of the circle? The tip of the electric vector rotates on the circumference of a circle. So, the field for a right circularly polarized wave propagating in the z direction, the electric field at this particular point, the electric field vector rotates on the circumference of a circle. That is a right circularly polarized electromagnetic wave. Now, the light from a sodium lamp or from an ordinary bulb is unpolarized. That is, the electric field oscillates, changes the direction at tremendous rapidity. But if you pass through a plastic like material, which is known as a Polaroid, the electric field that comes out of the Polaroid is along the one direction. So, what is happening is, this plastic like material has long chain molecules, and let us suppose they are all horizontal. Now, long chain, for example, there are iodine molecules, and the electric field generates a current along the length of the molecules, and it gets absorbed by Joule heating. Only the component which is perpendicular to the length of the long chain molecules pass through, and you obtain what is known as an X polarized light. These polarized sheets looks like something like a plastic sheet, and they are available in the market. All of you must be familiar with that. So, you allow the light beam, an ordinary unpolarized light incident on a Polaroid, the output is X polarized light. The electric field oscillates, let us suppose, in the vertical direction. Then if the electric field oscillates along the x direction, then this is known as a X polaroid, and the electric field after it comes out can be written in this particular form. If I rotate this Polaroid about the horizontal axis, then there will be no variation of intensity that will be seen, because this is unpolarized light. If I now put another Polaroid whose pass axis makes an angle theta with the x axis, then the light that is falling on the second Polaroid is X polarized. The electric field is in this direction, and the second Polaroid is oriented in a manner so that component along this passes through. So, the electric field component along this direction is E cos theta, and so therefore, the intensity which is proportional to the amplitude will vary as cos square theta. So, if theta is 0, almost the entire light will pass through, and if theta is pi by 2, then 0 intensity will pass through. This equation represents what is known as the law of Malus. So, for an unpolarized wave propagating in the plus z direction, this is the z direction, the electric vector which lies in the xy plane continues to change its direction in a random manner. That is what I have shown in the diagram on the left. If an unpolarized light beam is allowed to fall on a Polaroid, then the emerging beam will be X polarized. If we place another Polaroid P2, then the intensity of the transmitted light will vary as I0 cos square theta, and this law is known as law of Malus. Here I have tried to show two polarides which are parallel to each other. So, therefore, the angle theta is 0. Please notice the red dot and the blue dot at the top right hand corner of the each sheet, each polaroid sheet. So, the theta is 0, the two pass axes are parallel to each other, and so therefore, cos theta is 0. So, the entire light that comes out of the first polaroid passes through the second polaroid. If the angle between the two axes are 45 degrees, then cos square 45 is half, and half of the intensity will pass through. If they are made at right angles to each other, then the pass axis of one is at right angles to the pass axis of the other. You can see the blue dot has come here. So, they are at right angles to each other. So, almost 0 intensity passes through. This is a manifestation of the law of Malus. So, actual photographs with two polarides at different angles of relative orientation. If the two polarides are parallel to each other, almost the entire light passes through. When the two polarides are oriented at 45 degrees with respect to each other, about 50% of the light passes through. And when the two polarides are at right angles to each other, notice the position of the blue dot, almost no light will pass through. There are crystals like calcite crystal. If you put a calcite crystal on a piece of paper on which something is written, then you will see two images. This is known as double refraction. And indeed, if I have an unpolarized laser beam falling on a crystal, then the two emerging light beams coming out are linearly polarized, are always linearly polarized. This is one of the methods for producing polarized light. So, the wave theory, the electromagnetic wave theory of light, as was put forward by Maxwell, could explain many experimental observations, and by turn, as I had mentioned earlier, by turn of the century, people thought one finally understood what light really was, that light was indeed an electromagnetic wave. Then in the year 1905, when Einstein was working in the Swiss patent office, in the year 1905 he published 5 outstanding papers. That year is said to be Einstein's year of miracles, and the 5 outstanding papers were: the first paper was a method for determining the size of molecules, and the second paper was in which he put forward that light had a quantum nature, which I will discuss in a moment. In the third paper, he gave the theory of Brownian motion, in which tiny particles inside water move around because of the thermal motion of water molecules. And in fourth paper, he put forward the special theory of relativity, and in the fifth paper, he derived the equation E is equal to mc square. People say that each one of these papers was worth a Nobel Prize. So, in the second paper of his year of miracles, Einstein said that radiation energy, that is light, consists of indivisible quanta of energy, something like the corpuscular model put forward by Newton and others. And these quanta of energy, these packets of energy, was given by E is equal to h nu, that radiation must therefore, he wrote that radiation must therefore possess a kind of a molecular structure in energy, which of course contradicts Maxwell's theory. Wolfgang Pauli, a great physicist, later said that this was one of the landmarks in the development of theoretical physics. This paper was a landmark in the development of theoretical physics. So, using his corpuscular model, as most of you would know, he explained the photoelectric effect. Photoelectric effect, if ultraviolet light, what is photoelectric effect? If ultraviolet light falls on a sodium, potassium or a cesium plate, then electrons are emitted. The electrons that are emitted through this process are known as photoelectrons. And Einstein, using his quanta model, showed that the maximum kinetic energy of the emitted electrons, T maximum, represents the maximum kinetic energy of the emitted electrons, was equal to h nu, where h is the Planck's constant and nu is the frequency of the light that is used here, minus a constant B, which depends on the properties of the metal. For potassium it has a certain value, for sodium it will have a different value. So, this is usually referred to as the Einstein's photoelectric equation. Once again, T max represents the maximum kinetic energy of the emitted photoelectrons. So, this he wrote down in 1905, and very careful experiments were carried out by Robert Millikan, which verified Einstein's equation, this equation, to a tremendous degree of accuracy. So, on the vertical axis is the maximum kinetic energy of the emitted electrons, and on the horizontal axis is the frequency of the incident light. And the three lines shows the variation of the maximum kinetic energy of the electrons as a function of frequency of the incident light for cesium, sodium and copper. For each one of them there is a critical frequency nu c. If the light incident is of a frequency less than nu c, then no matter how intense the light may be, it will not be able to produce the photoelectrons. This was actually observed by Philip Leonard before Einstein's 1905 paper. And then he explained this photoelectric effect by using his quantum theory, by photon theory, and derived this equation. And this equation was very carefully verified by Robert Millikan. This is adapted from the Nobel lecture of Robert Millikan, and he made a very careful measurement of the maximum kinetic energy, and he found that to agree extremely well with Einstein's formula. So, you have the single photon source. Let us suppose you have one photon and the other photon comes and hits a polaroid of the type that I had talked about few minutes back. It produces what is known as an X prime polarized photon. Let us suppose this is the direction of X prime axis. Now, this is followed by a polaroid whose pass axis is along the X. So, this, will it pass through or will it not pass through? Wave theory says that the intensity should drop below by cos square theta. Quantum theory says that the probability of this photon to pass through the second polaroid is cos square theta. The probability that the polarized photon coming out of the polaroid P1, whose pass axis makes an angle theta with the x axis, that will pass through the second polaroid, whose pass axis is along the x axis, is cos square theta. So, one photon will pass through, another identical photon may not pass through. There is a certain probability that a polarized photon may pass through the second polaroid or may not pass through. The probability is cos square theta. Albert Einstein received the 1921 Nobel Prize in Physics for his services to theoretical physics and especially for his discovery of the law of the photoelectric effect. And so, therefore, Einstein got the Nobel Prize not for his theory of relativity, not for his theory of general relativity, not even for the concept of the light quantum, but for the Einstein equation, which was very carefully verified by Robert Millikan. And Robert Millikan himself received the 1923 Nobel Prize in Physics for his work on the elementary charge of electricity and on the photoelectric effect. So, after Millikan's work, Arthur Compton did a very beautiful experiment. He allowed high energy photons to hit the electron and get scattered by it. So, and then the electron undergoes a recoil and it moves in this particular direction. So, in his analysis he assumed that the light consists of packets of energy which are h nu, and its momentum of each photon is h nu by c, as Einstein had said, and when it hits the electron, the scattered electron will have an energy h nu prime, the scattered photon will have an energy h nu prime and the momentum h nu prime by c, and this electron will have a momentum given by mv. Using simple kinematics, that laws of conservation of energy and momentum, he could calculate the change in the wavelength of the incident radiation. So, this wavelength, the frequency of the scattered photon is little smaller. So, therefore, the wavelength is larger, and the change in the wavelength, which is equal to c by nu prime minus c by nu, he calculated this and found as 2 h by mu m naught c sin square phi by 2. And this is Arthur Compton writing on the blackboard his famous this particular formula. And this he did a very beautiful set of experiments in which high energy photons were coming out from an X-ray tube, they fall on a carbon target and the electrons and the photons get scattered at different angles. He measured the wavelength shift, and he compared with this expression and found excellent agreement. It was only after the work of Arthur Compton that people finally started believing in Einstein's light quantum, that light indeed has a corpuscular behavior and that its energy is equal to h nu and its momentum is equal to h nu by c. So, only after Arthur Compton's beautiful work on scattering of photons, one finally could believe that the energy of a photon is given by h nu and the momentum of the photon is given by h nu by c, where h, as we know, is the Planck's constant and c is the velocity of light in free space. Arthur Compton received the 1927 Nobel Prize in Physics for his discovery of the Compton effect. In 1926, Gilbert Lewis, an American chemist, coined the word photon to describe Einstein's localized energy quantum. So, therefore, let us suppose we have a sodium lamp. So, the number of photons emitted by a 50-watt sodium lamp in 1 second will be 50 watts divided by h nu. So, 50 watts is 50 joules per second, that is the energy that is emitted by the sodium lamp, divided by h, which is 6.6 into 10 to the power of minus 34 joules second, and nu, the frequency of a sodium lamp is about 5 into 10 to the power of 14 hertz. So, you multiply this out and you find that about 10 to the power of 20 photons per second. So, if a 50-watt sodium lamp is placed at a distance of 10 meters from a circular hole of 0.1 millimeter in radius, then from this tiny hole, about simple calculations will show about 40 million photons per second will come out of the circular hole. And so, therefore, this is a remarkable picture for series of photographs showing the photograph of a young girl with finite number of photons. The top left hand photograph corresponds to 3000 photons. Each spot here corresponds to 1 photon, and slowly as the number of photons increase, the last one corresponds to 28 million spots. Quantum theory gives us a probability distribution for the arrival of the photons. Where an individual photon will arrive, no one can say. One can only give, according to quantum theory, a probability distribution. And when you have very few photons, you will have few scattered spots, because you will always detect one photon or no photon. You can never detect half of a photon. But when you have a very large number of photons, like millions and millions of photons, then slowly the structure of the image will be obtained, which is consistent with the classical wave theory. So, physics with the advent of quantum theory has become probabilistic in nature. Classical physics is deterministic in nature, and I will give you one simple example of this probabilistic concept. Let us suppose you take uranium solid. Now, it has about say 10,000 atoms. It has a half life of, let us suppose, 1 day. Then you say that 5,000 will decay in 1 day. Then in the second day another 2,500 will decay. In the third day about 1250 will decay. So, see, all the atoms are identical, all the nuclei are identical. A few of them will decay in the first second, and some of them will not decay for days. Which one will decay when? No one can predict. And in fact, quantum mechanics allows you to predict the probability of decay and predict the half life of isotopes, as you indeed obtain in radioactivity. So, entire quantum theory is probabilistic in nature. The probability that the polarized photon coming out of the polaroid P1, whose pass axis is along the x axis, will pass through the second polaroid, is cos square theta. If the experiment is conducted with n photons, and if n is very large, then about n cos square theta photons will pass through. One can never predict the fate of an individual photon. Thus, the fact that the energy associated with electromagnetic radiation is quantized immediately leads to a probabilistic point of view. So, here is a very beautiful experiment. Here is a partially silvered glass plate which has 50% reflection, 50% transmission. So, you say half the light is reflected, half the light is transmitted. So, you carry out with a single photon source, one photon comes in. So, you say that half of them will go this side, half of them will go this side. That is not a correct statement. The correct statement is that a photon appears in this beam as well as in this beam, is described by a wave function which is present here and here. If I make a detection, if I put a detector, then it will be either detected here or detected there. There is a 50% probability of it getting detected by detector D1 and there is a 50% probability of getting it detected by detector D2. Let us suppose I generate the number 0 whenever the detector D1 clicks and I generate the number 1 when the detector D2 clicks. Then when the large number of photons are coming in, I will generate a set of completely random numbers. So, quantum theory, this simple experiment allows you to generate completely random numbers. Because of the indeterministic nature of quantum mechanics, we can generate true random numbers. Such a device is known as quantum random number generator. In fact, there is a company which sells these quantum random number generators and they cost about $1,000. And if you can read this, Quantis, this is the name of the product, is a random number generator exploiting an elementary quantum optics process. Photons are sent one by one onto a semi-transparent mirror and detected. The exclusive events, reflection or transmission, are associated to 0 or 1 bit values. The electron was discovered by J. Thomson in 1897, and now we know that the electron mass is known to a tremendous degree of accuracy, to 10 decimal places. The charge of the electron is also known to tremendous degree of accuracy. It can be bent by an electric field or a magnetic field. So, on the back of our mind, we think that it is a tiny particle with a definite mass and a definite charge. Louis de Broglie around 1923 wrote, "I was convinced that the wave particle duality discovered by Einstein." Einstein discovered the wave particle duality because he put forward the corpuscular nature of radiation, which was known to be an electromagnetic wave. So, I was convinced that the wave particle duality discovered by Einstein in his theory of light quanta was absolutely general and extended to electron, proton or any other. So, he said that the momentum of the photon is given by this. This was put forward by Einstein. So, this is equal to h by lambda. So, this relation, de Broglie said, has to be valid for electrons also. He predicted that. So, he said that P is equal to h by lambda is also valid for electrons, and that he justified by saying these are the Bohr orbits. This is the proton sitting at the center and these are the discrete Bohr orbits. As you all know, the Bohr orbits corresponds to MVR, the angular momentum, which is an integral multiple of h by 2 pi. N is 1, 2, 3, 4, h is the Planck's constant and divided by 2 pi. This implies that if I take 2 pi in this side, 2 pi r is equal to n h by mv, and mv is the momentum. So, n h by p, which is equal to h by p according to de Broglie, is the wavelength. So, he said that if I assume the relation lambda is equal to h by p, as was suggested by Einstein for photons. So, he said that if it is valid for electrons, then each Bohr orbit will contain an even number of wavelengths. So, he justified the expression, the de Broglie wavelength, through this analysis. and therefore, he said in 1923, that was his doctoral thesis, that lambda is equal to h by p is not only valid for photons, but is also valid for electrons, protons and photons. And this is the diffraction pattern. These were the experiments carried out in 1927 by Thomson and others, that diffraction pattern of aluminum produced by X-rays and by electrons. So, there is a tremendous similarity between the two. This shows that whatever the electron is, the photon is the same. So, the electron also demonstrated wave-like nature. So, de Broglie received the 1927 Nobel Prize in Physics for his discovery of the wave nature of electrons. And as you can see, de Broglie writing down the equation on the blackboard, lambda is equal to h by mv. So, the question arises, is the electron or a proton a wave or a particle? This is the fundamental questions. The correct answer is, it is neither a particle nor a wave. Then what is it? Quantum theory describes it by the wave function psi. And what is this psi? This psi is the solution of a complicated equation. I will not go into the details, but I will just briefly describe the solutions of this equation. But where did we get that equation from? Richard Feynman, who is considered to be one of the greatest physicists of all times, says, where did we get that equation from? Where did we get that Schrodinger equation from? The answer is nowhere. It is not possible to derive it from anything you know, and Feynman says it came out of the mind of Schrodinger. So, the electron or the proton or the neutron are described by the wave function psi. What is this psi? It is the solution of a complicated equation, and it cannot be derived. But the solution that you obtain by solving this equation agrees extremely well with experiment, as I will try to briefly show. So, Schrodinger received the 1933 Nobel Prize in Physics for the discovery of new productive forms of atomic theory. Actually, he shared the Nobel Prize with Dirac, and on his grave is written the famous Schrodinger equation. So, this is the solution of the Schrodinger equation. A free particle like an electron or a proton or a neutron is described by a wave packet. So, the electron is somewhere localized here, and as it moves, the wave packet moves, and it is a superposition of waves of different frequencies. So, or different momentum, and so therefore, if you do the analysis carefully, if a particle is localized within a distance of delta x, then it necessarily is a superposition of waves whose momentum spread is delta p, such that delta x delta p is of the order of h cross, which is the Heisenberg uncertainty principle. So, Heisenberg uncertainty principle is contained in the solution of the Schrodinger equation. So, let us suppose I have this electron falling on a potential barrier. Then I know that it is partially reflected and partially transmitted. Something like that, the beam splitter experiment that I did with photons, that light beam comes in, the photon is reflected as well as transmitted. So, according to quantum theory, the electron is here as well as there. And if you make a measurement, then it is either here or there. So, that is the most fundamental concept of quantum mechanics. Before the measurement, the electron is here as well as there, and this may be 1000 kilometers apart. It is described by a wave function which is finite here and finite there. So, there is a certain probability of making it found here or making it found here. But when you make the measurement, then it is either here or there. So, in the beam splitter experiment, you represent a photon by a light pulse, it is incident on the beam splitter, then there is partial reflection and partial transmission. So, the photon is here as well as here, and this may be millions of kilometers apart. But if I have a detector, then it is either detected here or detected there. So, I conclude by saying that if I have a electron beam or a proton beam or a photon beam, then wave theory predicts that there is a diffraction on a slit. The beam is, the electrons are incident on a slit of width b. The wave undergoes diffraction and the intensity distribution is sin square beta by beta square. Quantum theory, that is the solution of the Schrodinger equation for this particular problem, predicts that the slit imparts a momentum in the x direction. X direction is the vertical direction, and the probability that the x component of the momentum will lie between px and px plus dpx is the same as the intensity distribution. So, where does this momentum come from? It comes from the slit. The slit undergoes a recoil, and the electron undergoes diffraction. Smaller the width of the slit, greater will be the momentum that is imparted, and that follows from the solution of the Schrodinger equation. Similarly, I can do the double slit experiment, interference experiment. So, when I have an electron gun falling on the two hole experiment, the electron is described by a wave function which is present here as well as there. So, if one of the hole is open, you get an intensity distribution like this. Normally, you should expect that when both holes are open, the intensity distribution should be P1 plus P2, because the electron are tiny particles which either go through hole number 1 or hole number 2. But when you do the experiment, you get an interference pattern, and that can only be explained if the electron or the proton or the photon passes through both the slits at the same time. It is not the splitting of the electron, but that the electron is described by a wave function psi which is present here as well as here. So, therefore, this is considered to be the most beautiful experiment in physics. If you carried out this experiment with 10 electrons, you get 10 spots. Quantum theory gives us the probability. But if you did this experiment with 70,000 electrons, then slowly the interference pattern will develop. So, these experiments have been carried out by carbon 60 molecules also. So, the most fundamental theory now available is probabilistic in form and not deterministic. This is David Bohm, who is considered as one of the best quantum physicists of all times. So, this is the reference. Another reference is, this is my own book on optics, in which I have discussed all the experiments that I have discussed today and in my last lecture. But there is also this Feynman lectures on physics volume 3 that I would advise all of you to read through. Thank you very much.